now that we've looked at intramolecular forces, let's take a deeper look at intermolecular forces. Again, just to recall, intermolecular forces exist between different molecules. Now, one thing to clarify here, it doesn't necessarily have to be two different molecules of the same type. So for example, I could have water, which is H2O, and let's say HCl, right? There could be an intermolecular force between two different molecules. It doesn't matter if they both have to be HCl or they both have to be water, as long as there is an opportunity for there to be an intermolecular force, it is possible. Okay? And we'll learn about the different types of intermolecular forces and when it is that they appear. Right? So there are different types of intermolecular forces, and they don't necessarily have to exist individually. There can be a combination of different intermolecular forces, and we'll take a look later at them. So just to recall again, hydrogen bonds are an example. That is what's displayed in this picture here. You get to see the attraction between two different water molecules. And the different intermolecular forces that we're going to look at include hydrogen bonding, ion dipole, dipole-dipole, and London dispersion forces. So in each of these, we're going to see in which scenarios do these take place. So our first intermolecular force is hydrogen bonding. And this is a strong intermolecular attraction between a hydrogen atom and a very electronegative atom such as nitrogen, oxygen, and fluorine, right? So nitrogen, oxygen, and fluorine are among one of our most electronegative atoms on the periodic table, right? So when you take a look at these elements, their electronegativity numbers are quite high. So because of this, it produces a very, very strong inequality when it comes to the sharing of those electrons in that bond. Okay, so let me show you an example. Imagine you have a water molecule, right? And in this water molecule, like we've learned in the past, because oxygen is so much more electronegative than the hydrogen, there is what we call a dipole that is produced. And this dipole shows me that this has a partial negative, that this has a partial positive. And that exists on this side as well. So this oxygen has a partial negative, and the hydrogen has a partial positive. Now, knowing that, if there is another compound nearby that has a similar dipole, what do I mean by that? Let's show an example. So if I had an HF molecule here, this is also a molecule or a bond that has a dipole. So, except in this case, the dipole is going towards the fluorine. So I've got partial positive here and a partial negative here. Now, because in both of these bonds, there is such an inequality in the sharing of these electrons, this produces a very strong partial negative, and this produces a very strong partial positive. This attraction, right, between the hydrogen in one compound that's bonded to an oxygen to a fluorine in another compound that's bonded to a hydrogen, this is what we call a hydrogen bond, right? So this is still between different molecules. Let me just highlight that with a different color. So this taking place here, this is an intermolecular force. This is what we call a hydrogen bond. Now, it only exists between a hydrogen atom and a very electronegative atom, only nitrogen, oxygen, and fluorine. And this takes place only in polar molecules. This wouldn't take place in another molecule because there aren't any dipoles for this interaction to occur. All right, next we're going to look at something called ion dipole. So this is again an intermolecular force, but in this case it exists between a polar molecule and an ion. So say for example, I've got a polar molecule. Instead of drawing out the bonds, I'm just going to draw it in this oval shape. And on one side, I've got a partial negative, and on one side, I've got a partial positive, right? And if this is something like water, which is a solvent, and I want to dissolve something into it, something like NaCl. If NaCl is introduced into water, it breaks down into its ions. So the ions that it's going to form are Na plus and Cl minus. Now these Na plus and Cl minus are going to orient themselves all throughout that particular solvent, right? So when they arrange themselves, there is going to be an attraction between the positive ion or cation and the partial negative that exists in that particular solvent. So this is an attraction between an ion and a dipole, right? And the same exists for the Cl minus. Instead of it attaching itself or arranging itself close to the partial negative, it's going to arrange itself close to the partial positive, right? So there's going to be an attraction between the ion, which is here, and the dipole, which is here, right? And this is also another example of the ion, right? So depending on the charge of the ion and depending on the partial negative or the partial positive of the dipole, it's going to arrange itself in such a way that there is an attraction. Okay? So that is ion dipole. Now we're going to get into dipole-dipole. And the name, again, is very indicative of what this is. It is an attraction between two different molecules that both have a dipole. So let's take a look at our water and HCl molecules that I showed you earlier. So if I had water here, again, the dipole is pointing towards the oxygen, to our more electronegative atom. It's my partial negative, partial positive. And if I have something like HCl, right? So again, pointing from the less electronegative atom to the more electronegative atom. So partial negative, partial positive. Now there's going to be an attraction that exists between these molecules, and this, because this one has a dipole and this one has a dipole, this is what we call a dipole-dipole interaction. Okay, and this can only exist in polar molecules, right? Why? Because only polar molecules have a dipole. And it has to exist between these dipoles because it provides for an opportunity for that partial negative and the partial positive to have a attraction to each other. Okay, and lastly, we have London dispersion forces. And London dispersion forces are weak attractive forces that occur in all covalent molecules. So if we're identifying polarity of a molecule or not, as long as it is a covalent compound, we are going to have London dispersion forces. Okay, and these forces are very weak if you're looking for small molecules, but as the molecule size increases, if you're looking at larger and larger molecules, the London dispersion forces are quite strong. Okay, so those are the different intermolecular forces